In this talk, we're going to talk about our experience in building and operating a feature store for the last year and a half. And we're going to share some of our experiences and some of the things that we've learned along the way. So I'm going to start by telling you about Twitter, who run the feature store in production. And Twitter, along with many hyperscale AI companies, have been using feature stores to manage their machine learning assets. And one of their motivations for this is to increase the reuse of features across teams within the organization. So they actually introduced a metric which they call the number of teams who use another team's features in production, or the sharing adoption metric. And that's basically one of the ways in which they're evaluating their platform. Now, if you talk to any existing team who don't have platform support for machine learning assets, so data for machine learning, they don't have a feature store, this is the kind of reaction you might get. Now, this is a guy called Feel the Pain or Hide the Pain Harold. And Hide the Pain Harold, he's putting his thumb up and he's saying, great, of course I'll share my features with this other team, even though I have 500 million other things to do. He's saying he'll do it, but in reality he won't, because it's going to be painful. It's going to be painful because he doesn't have platform support for data for AI. Now, the main hyperscale AI companies that are out there, the likes of Uber, Airbnb, Twitter that I mentioned, Facebook, Netflix, they all have feature stores in production, and they've all talked about them. So there's a few links here you can follow to find out more about some of the existing feature stores in production. We at Logical Clocks have developed Hopsworks. It was the world's first open source, and it's still the only fully open source feature store for machine learning. And our feature store is running in production. And if you want to learn more about where it's running in production, you can go to the previous Spark AI Summit, the European one in 2019, where Swedbank talked about how they were managing 40 terabytes of data, transaction data, and they were doing fraud on it. So we're trying to detect fraud. And that particular, in that use case, we're managing the features for training models for predicting fraud in the feature store. And then we're using also the Hopsworks platform to train the models to classify transactions as fraud or not fraud. So what is the context here of what we're talking about? So I've mentioned that there's hyperscale AI companies have feature stores in production. So one of the things that we've seen is that existing data teams who have built out data infrastructure, so they've already maybe been, they've got a data lake, they've got maybe Delta Lake, Databricks, and they've built out BI tools. So what they've done is they've basically had to say, well, we've got all this data, we've got great infrastructure in place. How do we build this out to exploit AI? So this is where the feature store comes in. You need to take your data from all the places that it currently exists and write what we call feature pipelines. And the feature pipelines will transform the data in the data lake into features where the feature store will store it. And that data will be used for training of models, for serving features to online applications, and also for analytical applications that will use models to do analytics offline. Now, features themselves are not one homogeneous thing. You can have features that are entered by user, real-time features, and we have maybe less than 2 seconds to transform that input that the user's input into a feature for machine learning model, and that's something we've experienced with a customer. But a lot of other features have higher latency than the 2 seconds. Maybe they're historical data about user clicks, change data capture from an operational database, maybe user profile information, or some form of information collected by batch applications. So this data that comes in might have low latency, it might have high latency, but it's going to come into the feature store, and we're going to have these online applications, the data scientists creating trained data sets and batch applications using it. And they have very different requirements. The online application will need low latency access to the data, but as we saw with Swedbank, we might need many tens of terabytes of storage capacity, which is not what you would associate with an online low latency database. So the main thing that we have to take away from here is that nearly all feature stores actually are 2 databases. We can call it a dual database system. You have an online feature store for low latency serving of features, and an offline feature store to store scalable SQL data. And what we can see from this is that the pipeline where we're feeding our features into the feature store Now it needs to actually feed into both the online and offline. So we're introducing complexity. And that's really because there's no existing database that meets this need of scalable and low latency. And also being able to join features, because we want to reuse features, and that really means joining them. So what we did in our platform was we introduced this concept of a feature group, and it's really a data frame. So we have a Dataframe API where the features that are coming in, that are being ingested from these backend platforms, they're going to be read or cached in our feature store from Dataframe. So you'll have an application, maybe it's written in Spark streaming, maybe it's in Pandas, and that application will materialize or save its features in a feature group. So what our particular framework, the Hopsworks feature store, does is, by providing the Dataframe API, we simplify the complexity of storing that data in the online and offline feature stores. You don't have to, as a developer, have to worry about, well, is this going to online? Is it going to offline? How do I ensure they're in sync? How do I ensure the data made it to one but not to the other? And so on. So the feature group is an abstraction we introduced to simplify the usage of this feature store. So you may have noticed that this pipeline ends at the feature store, right? And the observant members of the viewers here will have said that this is not what we've heard before. We've often heard that machine learning pipelines are end-to-end pipelines. We go from the raw data to a model at the end. So in our case, when you have a feature store, you typically don't have end-to-end pipelines. What you have is a pipeline that starts at the back end where the data resides. So in your data lake, in your data warehouses, in your operational SQL systems, in your file systems, your object stores, and it ends up in the feature store. So in our case, in our platform Hopsworks, we use Airflow typically to orchestrate these pipelines. Often they'll be written in Spark, Scala Spark or PySpark. And when the features arrive in the feature store, and as we saw earlier, they may arrive at different cadences, they'll just end up there where data scientists can use them to actually write training pipelines. They're going to take the data from the feature store, those features, create training and test and validation data sets, and then they're going to use those data sets to train and evaluate their models and deploy them. So we use Airflow in our platform, again, for these training pipelines. So our feature store is built around the concept of features. And this example is from the Titanic data set. We have some features for uncovering whether a passenger has survived on the Titanic or not, and the sex of the passenger. But in this example, we can see there's a second feature group called bank accounts. So we're assuming that somebody has somehow discovered the amount of money people had in bank accounts on the Titanic. And it's now available in the feature store. So a data scientist can come along to this feature store, and the data scientist can say, well, I'm going to join a bunch of these features together. I'm going to take the Titanic passenger list features, and I'm actually going to augment it with this bank account balance, because I think maybe that will help me predict better if a passenger survived. Maybe they bribed to get on a lifeboat. So once the data scientists has decided on the features to join, they decide on a file format that they like to output the data as. So if you're going to materialize that training and test and validation data, you go ahead and say it's tfrecord for TensorFlow or NumPy for PyTorch, and then you decide where to store it. Maybe an S3 bucket, maybe on a file system. Everything here is versioned. So the features, the feature groups, and the training test data sets are versioned. So what does the API look like? We said it's a Dataframe API. Well, you're just reading in a data frame from a backend system. Maybe if you're doing derived features, you're reading from the feature store itself, and then you create a feature group. And that's really just putting in a description for the feature group, the data frame itself, and whether it's online, offline, or both. So we covered the ingestion of features to the feature store. That's on the left-hand side. Now we'll just look briefly at how we use the feature store. So we'll look at online applications and then creating training test data sets. So creating a training test data set with our feature store, originally we had this flat namespace of features. So we can see we have this sample underscore data, which is a data frame we get by joining these features together. And the query planner in our feature store would look for a common join key across the feature groups, give you back the data frame. We can use it directly, or we can materialize the data, output it as tfrecords. And we can see the formatting is slightly off there. The online feature store, which is another user of the feature store, will use the feature store to get features in real time. So this online application is going to say, hey, you know, I have a transaction, I want to classify it as fraud or not fraud, and I have a bunch of input data. I have the IDs of the customers involved, the banks involved, the amount of money, the date. Now I need to go to the feature store to get a lot of historical features. So number of transactions users have done, you know, and so on. Could be even hundreds of features. So in our case, we use the online feature store MySQL cluster, and we basically pass those keys to the feature store, and it performs the join then. We're using a JDBC API because it's kind of language independent and it's also low latency. And what the application will get back is a feature vector that it can use to send to a model for prediction. So typically models will be served over the network. Maybe it's TensorFlow serving server or Flask server. And in our case, we've set it up so that everything is highly available. So in the cloud, it typically then both this online database and our model serving will be highly available across availability zones. I'm going to hand over to Fabio at this stage. We'll talk about what we've learned between this first version of the feature store and the new version that's coming out now.
So thanks, Jim. So far, we have seen how we work with the feature store API version 1, and the APIs have been out for over a year now, and we have learned several things. So we would like to go through what are the good decisions that we took in designing API v1, and the shortcomings, and how we solve these shortcomings in version 2. So regarding version 1, I think there are some like 4 aspects that we did right. We took what we believe are good decisions. First one is we built the APIs around the concept of data frames. We didn't build around the concept of DSL. DSL could be added later. The main reason is that it's really hard to get to DSL, a general purpose DSL right. There are some companies that already are building internally a feature store, and they have a DSL internally for this specific use case, but to generalize it, it's quite complicated. The second step is that we see the feature store as cache for materialized features, not libraries. A library is good if you want only to enforce that the same code that is used to generate features during training, it's the same code that's generated features during serving. But as soon as you start hitting limitations in terms of latency when serving features, you soon realize that you have to materialize these features. And even if you don't have this online serving aspect in your pipelines, even if you're doing just fetching, you soon realize that it's more useful and less expensive to materialize the feature computation instead of computing features over and over again. And this brings us to the third point, where basically separating the use case for online and offline onto different databases, so we can serve both low latency and batch jobs efficiently. And finally, the key component of the feature store are features. And features are the building blocks you can use to build trained data sets, and you can share them, you can reuse them across multiple trained data sets. And this means that you need to join features across with other features. And this means you need an engine that can do joins. And in our case, is Spark. What are the shortcomings of the API v1? The first one is that we try to do like a flat namespace, as we were saying before. The issue is that as soon as you start hitting as soon as you start scaling your feature store, onboarding new teams, adding features and so on, you hit name conflicts where you have 2 teams having the same feature with the same name, but represent 2 different things. And so we introduced the concept of feature groups to scope out and basically solve these kind of like naming issues. The second point is like, by talking to the users and customer, we've seen over and over again that people want to have production feature store where basically only Airflow pipelines or like predefined pipelines can write into this production feature store, and let data scientists and the engineers play with like new features and new experiments on a development feature store. At the same time, people want to allow data scientists and the engineer to join features between development and production feature store to build up actual trained data sets. So with this in mind, we actually improved the joining capabilities to allow people to join better features from different feature groups, from different feature stores, and be more expressive when define joins. And we'll see that on an example. We also have a first-class support for time travel for feature groups, so you can go back in time and see exactly at which stage, any point in time, what the feature group looked like, and get also the changes that apply that were applied to this feature group. And finally, we try to be more consistent with other frameworks that are out there, meaning PySpark and Pandas Dataframes, basically. So this is what I was referring before. So this we have a demo later on where we basically go through in more details. But this was the idea that I was telling you before, where we try to work with the production and development feature store. So we get a connection from an instance running on Hopsworks AI, and we get two handles, one for the production feature store and one for the development feature store. And using those handles, we can reach the feature groups that we are interested in and join them together. Regarding the feature groups, nothing much has changed related to the first version. You create in the first instruction, you create a metadata object that lives within your application only, and then you save this. And when saving, you pass a data frame, and the library passes the schema data frame and uses the columns of the data frames as featured, and gonna persist at that moment the metadata in the feature store. Of course, you can call read, you can add more data afterwards, and in particular, you can also make this feature group available online by setting the online enabled flag to true. One thing we added in this new version is we added support for tagging. If you have thousands of features across thousands of feature groups, you can easily add tags to them. You can define tags across multiple feature stores, so production and development, and you can tag features and feature groups entering this set. And the platform is going to index those tags and allow you to do free text search on those tags. One more thing we added is that we added support for schema changes, non-breaking schema changes that do not require increasing the version. So feature groups entering a set of versions, and the versions are meant to represent breaking changes. So you remove a feature or you change the meaning of a feature, and this makes that, like, if you increment the version, existing pipelines that rely on that feature being there, or existing models that rely on that feature being computed in a certain way, do not break. However, like, if you want to just add a feature, this is not a breaking changes, and we can do that now on the same feature group, same version, without asking you to bump the version. When I'm like, if I put my data scientist hat on and I'm doing like I'm exploring the feature groups at the feature store and looking for features that I can use. We try also in this case, as I was saying before, to be as similar as possible to existing frameworks like PySpark and Pandas. So as you can see here, I can pretty much do the same operations that I can do on PySpark Dataframe. So I can select a bunch of features from a specific feature group, from a specific feature store. I can call show on them. I can read. I can filter for a specific value. And yeah, this is pretty much the same as a PySpark data frame. When it comes to join, this is an example that we try to give as much as opportunity to data scientists to express their join in a familiar way, like in the Pandas data frames. So in this case, in this example, I'm trying to join 3 feature groups together, one coming from the production feature store, and 2 coming from the development feature store. So I get the handle for all of 3, and I select some features from all of them that I'm interested in, and I can join them together. So I can decide to pass and provide a joining key, as in the second join, or I can omit the joining key. If I omit the joining key, then the feature store will automatically figure out what is the largest subset of primary keys from the different feature groups, and use those to join. And of course, I can overwrite this behavior. I can also overwrite the behavior of which kind of joins to apply. By default, it's an inner join, but you can also overwrite it to be a left join or whatever other join. And finally, I can build up a data frame and see the result. When looking at the data exploration, I can also use the time travel feature of the feature store. So I can go and fetch a feature group, and I can specify either a time. So what did the feature store look like at X time in the past? Or I can specify a range, and the range will give me back the changes that happened on that feature group during the time range. And finally, we create a training data set. So to create a training data set, I get the query that we built in the previous slides, and I apply and create a training data set with that. The same is a similar concept to the create the feature group. So I call the create method. We now have support for automatically defined splittings. So we can split the training data set in as many splits as we want. In this case, for instance, training, test, and validate. As in version 1, we can save the training data set on HDFS, or we can save it on external system like S3 bucket. You can specify the data format. And again, we call save on the training data set object, and we pass the query. We pass the query, and the query is going to be reused when we are doing inference. During inference time, we want to augment our inference vector, and the feature store can help us in that sense. So we can ask the feature store to get the feature vector for a specific training data set, and this will return the set of features in the order that we used during training and the query. So you can then go to the online feature store and select the entries from those feature groups from the online feature store. You can also specify a set of JSON objects to restrict the specific entries that you are interested on. Okay, so in this demo, we're going to see how we can work with the HDFS library and the feature store API to interact from a Databricks cluster with the Hopsworks feature store. So I already went ahead and created an instance on Hopsworks.ai, and at the same time, I already created and configured a cluster on Databricks, installing the necessary libraries and applying the necessary Spark configuration. All the instructions are available in our documentations. We have a section describing how to configure your Databricks cluster, and you can check it out at hopsworks.readerdocs.io. So if I go on my notebook, as a demo notebook, the first thing we have to do is to get a connection for the specific feature store we are working with, passing the location and the project we want to work with, and how to fetch the API key to authenticate with the feature store. At the same time, we have to get an handle for the specific feature store we want to work with, in this case a development one, but at the same time we should, if we want to work with the production one as well, and join feature groups between the two, we also need to get an handle for the production feature store. In the next steps, we're going to do some basic feature engineering. We're going to work with a CSV file containing weather measurements from weather stations in Australia. So we're going to create 3 data frames. One is going to be a location data frame. It's going to be a lookup feature group, basically containing location as a string, the city, and location as a random ID, basically for each city. We also do build up a feature group for temperature, and we're going to do a bunch of features which are temperature related, and some aggregations on them, and the same thing for rain and aggregation related to rain. Here finally we create the feature groups on the feature store. The first thing we have to call is this create feature group. This is equivalent of spark.create data frame. So at this stage, nothing gets persisted on the feature store. It's only creating a metadata object within the application. We pass a name, we pass a version, we pass a description, and we pass a primary key, which means that all entries in my feature group will be uniquely identified using location ID. And finally, we call the save. And this stage will actually parse your data frame object and use the columns of the data frame as features, and it's going to persist everything in the feature store. We do the same for the temperature feature group. In this case, we also pass a partition key, which allows you to control how data is actually written on disk, which is going to be useful if you start doing optimization in joining and so on. And again, we save it, and we do the same for the rain feature group. So if I now put my data scientist hat on and I want to explore what's available on the feature store, I can call this get feature group. And get feature group will get me I have to pass a feature group name, which is case of rain, and the feature group version. Version is not mandatory. If you don't provide it, it's going to default to 1. I can get some metadata, and I can also get some of like a sample of the data. All of this is also available from the UI. In particular, you can see the same sample data from the UI. You can, if the feature group was partitioned, we could select a specific partition. If it was also available online, we could select to see sample data from the online feature store. Let's go back. Yes, so now we want to build a query, and the query is basically the entry to be able to create a training data set. And to do that, we also get the handle for the temperature feature group. And we can do a simple query and join temperature and rain features together. Again, we just select all, and we don't have to pass any joining key. The feature store is smart enough to figure out that both of them have the same primary keys and use them to be able to join them. But if you want to override this behavior, then you can pass your own joining keys, and you can also pass your the type of the join, basically. You can also not select all the features and select only a subset of them. You can go in the feature store UI, and you can select a specific. You can see the schema and pick whatever features you actually need and use them in your query, basically. You can execute the query against the online and offline feature store, and you can use the query to create the training data set. So same as for the feature groups, create training data set doesn't create anything. It just creates some metadata object within the application itself. And when you create a training data set, you can also pass, besides name, description, and version, you can also pass like how to split the training data set, and if you want to have train, test, validate, for instance. And when you save it, you can also overwrite. You can also overwrite the some write option. So in this case, instead of having a command, I want to have a pipe between the different columns. One more thing I want to show you: if you work with a lot of feature groups and a lot of features, it becomes quite hard to then find them. And for this, you can use tags. So you can define tags at cross production and development feature store, and you can select a feature group or a feature or a training data set, and you can apply a specific tag. In this case, I already apply a country tag and a year tag, so Australia in 2010, and then I can search for them. So if I go and search for Australia, then I can see that in the development feature store there is a feature group with a tag called Australia, and then I can go and inspect it, and I can see that I can go back to some UI and see the schema and so on. So yeah, if you want to try it out, the feature store and the Databricks integration, I suggest you check out Hopsworks.ai and our documentation, hopsworks.readdocs.io. Thank you very much. If you want to learn more, you can try it out on the Hopsworks feature store from Hopsworks.ai. You can have a look at the open source code in our GitHub repository, logicalclocks/Hopsworks. You can follow us on Twitter @logicalclocks. And I would like to take this opportunity to also thank my colleagues for their contribution to the feature store. Thanks.